Welcome to qnawire.
All right. So recall that the force on any sort of electrically charged object is equal to K, which is just a constant, right? And then we've got Q, which is the charge of object 1, Q2, which is the charge of object 2, and then the, uh, the square of the distance between them. And then this isn't currently taking into account directionality, um, but that's another something that you have to take into account, right? This is just purely the magnitude of the force, if you will, right? Um, and then you can basically just use this and figure out magnitude from directionality from context, right? So let's begin with this first one. If I've got -2 here and -1 here and -1 here, right? And the distance here is 2 and the distance here is 2, right? So we're interested in the force on this object in the middle, okay? So let's consider the force exerted on the object from the charged particle on the right, right? They're both negative, and the charged particle is to the right, so it's going to be pushing to the left, right? And the magnitude of that force is going to be -2 times -1 divided by 4, right? That's 2 squared, right? So it's basically going to be the magnitude is, without any real units, let's just say it's a half. And similarly, because this is the same charge and the same distance, it's just on the opposite side, we're going to have a force pushing on the right with a magnitude of 1/2. And so the net force is actually going to be 0, right? Because we've got equal and opposite forces pushing on this the thing charged in green. So the center option is your option. There's no force. There's no net force, we should say. Okay, let's move on to the next one. Now we've got a charge of +1 in the middle. 2 to the right, we've got a charge of +3. And 1, 2, 3, 4, 5. Looks like 7 to the left. We've got a charge of +1. Okay. So let's consider what the force on this central dot is coming from the right. Right, we know it's going to be the net force, right? It's going to be K, some constant that we can ignore, Q1, Q2, over the radius squared, or the distance between them squared. Right, so it's going to be pushing to the right with a magnitude of 1 times 3 over 4, or 3/4. Right? And what about from the left? Well, it's going to be pushing on it to the right, but the magnitude here is going to be much smaller. It's going to be 1 times 1 over 49. That's 7 squared. So this is going to be 1/49th, right? So overall, right, it's kind of like saying, what's 3/4 minus 1 over 49, right? It's going to be positive to the left, right? The net force, right? If I tried to draw this to scale, maybe that would help. Like this force is like that, and then this force is like that, right? So the net force, say I drew this in blue, we would just subtract this much. And so the net force would be what's ever left over after we cancel out this 1/49th. So the net force is going to be to the left. Okay, last one. Now we've got a charge of +3 in the middle. And 1, 2, 3 units to the right, we've got a negative charge. And 1, 2, 3, 4, 6 units to the left, we've got a -1 charge. Okay. And we're interested in here. Okay. So now the force from the object on the right is going to be attractive, right? So it's going to be pointing to the right. And the magnitude, this is 3, this is 6. So the magnitude of the attractive force to the right is going to be 3 times 1 over 9 equals 1/3. And to the left, it's going to be less than that. It's going to be 3 times 1 over 36, or 1/12, right? So the force to the right is dominating. The force to the right is larger, so the net force will be to the right.